String searching is the operation of searching for a string in another one. Intuitively, what we would do to perform the operation is to start from the first index of S1 and see if S2 matches. If it doesn't match, we start again from the second index. If it doesn't match, we start again from the third index, and so on until we find it. This method is called the brute force method. But the problem is that in the worst case, we traverse the whole characters of S2 at almost each index of S1. For example, here we have A, then a mismatch. We start again from the second index, A, then mismatch. Third index, A, then mismatch, and it continues like that. This is why we got an O of n times m time complexity, where n and m are the lengths of S1 and S2 respectively. In the worst case, we traverse the m characters again for each one of the first n minus m plus 1 indexes of S1. O of n m time is slow for string searching. Let's see how we can optimize it. Let's take this example. We start from the first index, we have A, then here characters don't match, so we need to start searching again. First question, in the brute force solution, why did we start searching again from the next character from where we started? Why didn't we just continue from the actual index I? We would avoid losing time on always going back in S1. Take some seconds to think about it. It's true that when we started from the first index of S1, it didn't match S2. We found a mismatch at index 5. Now we need to start searching again. But if we decide to start from the actual index, we may miss a prefix that would lead us to the match we're searching for. For example, here if we just start from I, we have a match, then we have B and A mismatch, we start again B and A mismatch, we start from the next index C and A mismatch, we start from the next index B and A mismatch, and we finish traversing S1 without finding S2. We would say that S2 is not present in S1. It's because we skipped an important prefix of S2, which is A. You can see that at the mismatch position we already matched with A, and if we just continue from after A, we have A, match, then B, match, then C, match, and we finished S2, so we found the match in S1. And this is why in the brute force solution we always go back from where we started and we move to the next index to start from there, to avoid skipping important prefixes that we already matched with before. But always going back is kinda slow, we need to optimize it. In the last example, when we found a mismatch, we could notice that we already matched with A before. This is why we didn't take I back, we just started after A in S2, and we could continue matching. Knowing that we matched with A is what gave us the ability to avoid losing time when going back on S1 and traversing again the same characters. So the idea is that instead of taking I back to where we started, we just check what prefix we already traversed and start again from it. For example, in this situation, okay, there is a mismatch, but we already matched with A. We start from index 4 in S2, because the length of A is 4. But the question is, why A and not another one? First of all, A is not the only prefix. We also have A, and the empty string. We took A because it's the longest proper prefix. We take the longest one because we want to avoid traversing again as much characters as possible. I said longest proper prefix. What does proper prefix mean? A proper prefix of a string S is a prefix of S that is different from S. It's true that S is a prefix of itself, but it's not considered as a proper prefix. The proper prefixes of S are prefixes of S minus S. We take the longest proper prefix because in reality the longest one is the whole string itself, the part we already matched, and if we take it, we know that it won't lead us to the match we're searching for, because we found a mismatch. This is why we take the longest proper prefix. Next question, how did we know that it's A and not something else? We started from the first index and we matched with the part A, then we found a mismatch. Let's name the part that matched S3. We're searching for a proper prefix of S3 that is as long as possible, but don't forget that it has to also be a suffix of S3 in S1, because we will continue from the right, and characters must be adjacent. In brief, we need to search for the longest proper prefix of S3 that is also a suffix. In our example, it's A. It's not that clear with this example, let's take this one. We start from the first index, we have A, B, D, C, A, B, then mismatch. Here, the longest proper prefix that is also a suffix of S3 that we traversed before is AAB. By traversed before, I mean that ends at the end of S3 in S1 to be able to continue taking characters. We take J to the position just after it in S2, then we take D, C, A, B, C, D, B, and we found S2 in S1. You can see that we took the longest proper prefix that is also a suffix of S3, we skipped its characters to avoid losing time, and we continued matching without taking I back. In brief, when we find a mismatch, we search for the length of the longest proper prefix that is also a suffix of the path that matched to know how many characters to skip when we start searching again. But searching for the longest proper prefix that is also a suffix of a string of m characters costs O of m time, and by doing it at each iteration, we would get the O of n times m time complexity again. It's like we did nothing. But what if instead of always losing O of m time to compute the length of the LPS, we compute the length of the LPS for each part of S2 at the beginning, we put the result in an array so that when we start working, finding the length of the LPS will cost O of 1 only. We just take the value from the array. And that's what the Kmp algorithm does. It starts by doing some pre-processing to create the LPS array, an array where LPS of k represents the length of the longest proper prefix that is also a suffix of the first k+1 characters of S2. Then, it starts working on S1. For example, if S2 is equal to this string, in LPS array we'd get 0, 1, 0, 1, 2, 2, 2, 3, 4, 5, 3. But how to actually compute these values? That's what we will see now. We have a brute force solution for finding the length of the LPS for each part, but we want to have an optimized solution. We will try to do it in O of m time only, not more. We create an array of m elements and we start. When we have one character only, the only proper prefix is the empty string. Its length is 0, so LPS of 0 will always be 0. And now the idea to fill remaining cells is that if we know the LPS of the first k characters and we want to know the LPS of the first k+1 characters, we compare the character k+1 with the character just after the LPS. So we will use the LPS of the first k characters to find the LPS of the first k+1 characters. For example, if we have this string and we're at this position, the LPS is AB. Now if we want the LPS of the path that ends one position after it, we increment both I and j and we compare. Here s of I and s of j are equal, so we can extend the LPS of the previous position. The LPS of this position is ABA. Next iteration, after incrementing I and j, here s of I and s of j are also equal. We extend, the LCS of this position is ABAA. Next iteration, same thing, we extend, the LCS of this position is ABAAB. Next iteration, here they don't match, we cannot extend. But we don't start again from the beginning, we check the LPS of the path that matched. Here the path that matched is ABAAB, the length of its LPS is 2. We could know it from the array by checking the cell j-1 of the LPS array, which is 2, so we take j to 2. Note that we have no problem to find the LPS of the path that matched because we already computed it. Now s of I and s of j match, we can extend, the LPS is ABA. Next iteration, s of I and s of j don't match, we check the LPS of the path that matched. The path that matches ABA, the length of its LPS is 1, we take j to 1. S of I and s of j don't match, and the path that matches A, its LPS is the empty string, the length is 0, we take j to 0. S of I and s of j don't match, and here j is 0, it means that we just don't have a proper prefix suffix except the empty string for the path that ends at I. We just put 0 and increment I to start again from the next position. Then here s of I and s of j match, we extend, the LPS is A, we put 1. And we continue like that until we finish traversing the string. From this example, we deduce that at each iteration, we compare s of I and s of j, and we have 3 cases. The case where they match, the case where they don't match and j is greater than 0, and the case where they don't match and j is 0. When they match, we can extend, we increment j, which is also the length, we put it in LPS of I, and we increment I to move to the next cell in the array. When they don't match and j is greater than 0, we take j to the length of the LPS of the path that matched. And when they don't match and j is equal to 0, we just put 0 in LPS of I and increment I to start again from the next position. Because the LPS is the empty string, there is no other choice. Let's continue our previous example now. J starts at 0 and A at 1. 1 because we already filled LPS of 0. Here they match, so we extend. The LPS is A. Next iteration, S of I and S of j don't match, and the path that matches is A, its LPS is the empty string, the length is 0, we take j to 0. Here again they don't match, and j is 0, we just put 0 and move to the next value of I. Here they match, we extend. The LPS is A, its length is 1. Next iteration, here they match, we extend. The LPS is AA, its length is 2. Next iteration, here they don't match. The LPS of the path that matches A, the length is 1. We take j to 1. Here they match, we extend. The LPS is AA, the length is 2. Next iteration, same scenario. J will be taken to 1, then they match and we get AA as LPS. Next iteration, they match. The LPS is AAB, length is 3. Next iteration, they match. The LPS is AABA, length is 4. Next iteration, they match. The LPS is AABAA, the length is 5. Next iteration, they don't match, and LPS of the path that matches AA, its length is 2, so we take j to 2. Here S of I and S of j match, we extend. The LPS is AAB, we put 3. Now I reached the end of S, so we finished filling the LPS array, we return it. In code, we create an array LPS of length of S characters, we initialize I and j to 1 and 0 respectively as done earlier, then while I didn't reach the end of the array, we have 3 cases. If S of I is equal to S of j, then we can extend. The length of the LPS is just j, and we increment both I and j to move to the next iteration. Note that we incremented j before assigning j to LPS of I to get the right length. Second case, they're not equal and j is greater than 0. Here we said that we take j to the length of the LPS of the path that matched. The path that matched is in reality the part of S that ends at j-1, and the length of its LPS is in LPS of j-1, so j is equal to LPS of j-1. And last case, when they're not equal and j is 0, we just put 0 in LPS of I and we increment I as explained earlier. After filling the LPS array, we just return it. Now that we know how to generate the LPS array, we can use it for the Kmp algorithm. Let's take this input for example. The first step is to generate the LPS array of S2, the string we're searching for. And S2 is the same string as the last example, so we get 0, 1, 0, 1, 2, 2, 2, 3, 4, 5, 3. Now let's start from the first character of path. They match, we continue. They match, we continue. Now S1 of I and S2 of j don't match, and the path that matches AA. Its LPS is A, its length is 1, so we take j to 1. Now they match, next iteration, they match, next iteration, they match, next iteration, they match, and next iteration, they don't match. J is 5, so the path that matches AABAA, its LPS is AA, its length is 2, we take j to 2. Note that here we're using quite the same logic as when filling the LPS table. When characters match, we increment both I and j. When they don't and j is greater than 0, we check the LPS of the path that ends at j-1 and we take j to its length. And when they don't match and j is 0, we just increment I to start again from the next position of I. Also, you can notice that we are able to get the length of the LPS directly from the array. We're doing it in O of 1. We can say that we're able to do what we wanted to do since the beginning of the video, searching without taking back I to avoid losing time and getting the length of the LPS in O of 1 time. Let's continue. Here they match, next iteration, 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 they don't match. The path that matches is AABAAA. Its LPS is AA, whose length is 2, we take j to 2. Here also they don't match. The path that matches is the one that ends at j-1, which is AA, its LPS is A, whose length is 1, we take j to 1. Here they match, next iteration they don't match. The LPS of the path that matches is A, its length is 1, we take j to 1. Here they don't match again, the LPS of A is the empty string, its length is 0, we take j to 0. they don't match again, and j is 0, we just increment I to start again, we have no choice. Here they match, next iteration they match, next iteration they match, next iteration they don't match. The path that matches is AAB, its LPS is the empty string, the length is 0, we take j to 0. Here again they don't match, and j is 0, we just increment I. Now it matches, next iteration it matches, next iteration mismatch. The LPS of AA is A, holds the length is 1, we take j to 1. And from here we have match, 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 and we reach the end of S2, so we've been able to find S2 in S1, we return I minus M, which is the starting position of S2 in S1, which is what we're switching for. In code, we put the length of S1 and S2 in N and M respectively, and now we have some early exit conditions. If S2 is longer than S1, then we cannot find it in S1 obviously, we darkly return -1. -1 means that we didn't find it. Else if S1 and S2 have the same length, if they're equal, we return 0, the index of the first character because it starts from there, and -1 if they're not equal, because if they have the same length, the only way to find S2 and S1 is by starting from the index 0 and all characters match. Else if S2 is the empty string, we darkly return 0, because the empty string is a substring of any string. Now we can start. First of all, we saw that we do some pre-processing to generate the LPS array of S2. We just call the function we made earlier, getLPS. Now that we have the array, we put I and j as the first character of S1 and S2 respectively, 0, 0, and we start looping. The loop stops when we reach the end of either S1 or S2. Reaching the end of S2 means that we found it in S1, and reaching the end of S1 without the end of S2 means that the search was unsuccessful. Now we have the same three cases as when filling the LPS array, but without assigning to an array because we aren't filling any array. If S1 of I and S2 of j are equal, we just increment both indices. We increment I and we increment j to move to the next pair of characters. Else if they're not equal and j is greater than 0, we say that we take j to the length of the LPS of the path that matches, the one that ends at j-1. And its length is an LPS of j-1, this is why we assign LPS of j-1 to j. Else if they don't match and j is 0, then we can't find S2 by starting or passing from I, because even the first character doesn't match, so we just increment I to start again from the next position. The second case, when we take j to LPS of j-1, is what we've been explaining in the beginning of the video. It's a really important point that you need to understand. It's what gives us the ability to not take back I. We said that from the LPS array we can darkly know how many characters we can skip. This is why we take j to it. J in reality represents the first index from where we should continue comparing. After the loop, if j is smaller than m, then we return -1 because it means that we didn't find it. Else if we found it, we return I minus m. I represents where we found the end of S2 and minus m to go back to the starting index, because we want the index where S2 starts in S1. And that's how the Kmp algorithm works, an interesting string searching algorithm that takes advantage of the longest proper prefix that is also a suffix of the path that matched to be able to skip characters and avoid losing time when traversing them again. Ask me in comments if you didn't understand something. Okay, now we know how the algorithm works, but what about its time complexity? For the time complexity, let's first start by analyzing the getLPS function. We want to generate the LPS array of a string of m characters. Creating the array costs m, then for the loop, we're traversing the m characters with an index I, so we may think that the loop will do m iterations. But you can notice that I isn't getting incremented at each iteration, so we may have more than m iterations. Because of that, we may think that in the worst case, each value of I requires O of m iterations before it gets increased, which would result in an O of m squared time complexity. But no, let me explain. The second case is the one where I doesn't increase, and to occur, j has to be greater than 0. And to have j greater than 0, it must have been incremented before. J gets incremented only when characters match, where we also increment I. We deduce that we can't have the second case without incrementing I. We also know that in the second case, j can only decrease when we assign LPS of j-1 to it, because LPS of j-1 is always smaller than j. From these 5 statements, we deduce that because I gets incremented m times before the loop stops, it means that the number of iterations where the second case occurs is at most m. In total, we have m iterations where I gets incremented and m iterations where it doesn't. We got at most 2 m iterations for the loop. Plus m for array creation, we get 3m, which gives an O of m time complexity for the getLPS function, where m is the length of the string passed as an argument. Now for the Kmp function, we have O of m for calling the getLPS function. Then for the loop, we may think that in the worst case we do n iterations. N because n is greater than m, because cases where n is smaller than or equal to m are handled by early exit cases. But here also, we have a case where I doesn't get incremented, in the second case to be precise, so we may have more than n iterations. But same logic as for getLPS, to form the second case, j must be greater than 0, in other words, it must have been incremented before, which is not possible without also incrementing I. And I is incremented n times during the process, so the number of iterations where it doesn't get incremented can't exceed n. In total, in the worst case, we have n iterations where I is incremented and n iterations where it doesn't. N plus n is 2n, which gives O of n. So we have O of m for generating the LPS array, O of n for the loop, we get an O of m plus m time complexity for the Kmp algorithm. And for the space complexity, it's O of m because of the LPS array. Note that even if the Kmp algorithm has an O of m plus m time complexity, it doesn't mean that it's always the best choice when it comes to string searching. It depends on the length of the two strings, overlapping substrings, and other factors. This is why there exist situations where we would use another string searching algorithms like Kmp and More. We reached the end of this video. I hope that I've been able to explain to you the Kmp algorithm. Give me your feedback in comments, like and subscribe to the channel, and see you in the next one.